Okay, now we want to look at a couple of examples evaluating limits numerically. So the previous examples that we saw, those were evaluating limits graphically. So that's sort of the imprecise option number one was graphical, and the imprecise option number two is the numerical method. So let's look at an old function that we've seen already. This funny looking piecewise defined function x squared minus 1 over x minus 1 when x is not equal to 1, and then 0 when x is equal to 1. So we drew a picture of that, and we saw what it looked like. So this thing we kind of reduced and said, okay, it looks like x plus 1 except at 0. And so we saw that the function looked something like this, right? So we had this deleted point at x equals 1. So how can we compute the limit numerically? Well, it's basically the same thing that we did in finding the successive average rates of change. Make a table, plug in a few values of x that are close to 1, and we want to make sure that the values close to 1, some of them should be a little less than 1, some of them should be a little greater than 1. So we'll get a list of x values, plug it into the function, use a calculator, and see what we get, and then make an estimation. Okay, so to evaluate this limit numerically, we just want to fill in a table with some numbers. So look at these x values. They are all to the left of 1, and they are all very close to 1, at least by the time we get to the end. So this table will show us the left-hand limit as x approaches 1. This table, again, all of these x values are greater than 1 and close to 1, so this table will show us the right-hand limit as x approaches 1. Now, we could just factor and cancel, or sorry, we could just plug in the numbers right away using a calculator. It will make our computations much easier instead of squaring, subtracting 1, and then dividing. Let's make our computation easier by factoring the numerator and canceling. So instead of plugging all these x values into this nasty expression, we really just need to plug the x values into this thing. And here, if we cancel first, we can almost just do this by inspection, right? So when I plug in 0.5, I get 1.5. Here I get 1.9. Here I get 1.99. And then finally, 1.999. So it looks like the left-hand limit, so it looks like the limit as x approaches 1 from the left, looks like we are getting closer and closer to the number 2. And then do the same thing here. So I could plug in all of these x values into this thing, or I can simplify my expression and write x plus 1, right? These two functions are equal as long as x is not equal to 1. None of these values are equal to 1. Same thing here. As long as x is not equal to 1, that's fine. None of these values are equal to 1. They get mighty close, but they don't ever equal 1. So this is fine. So again, I'm going to plug these numbers into x plus 1 instead of x squared minus 1 over x minus 1. So here I get 2.5, 2.1, 2.01, and then 2.001. So again, it looks like the limit as x approaches 1 from the right of our function here, again, is about 2. Therefore, the limit as x approaches 1, the two-sided limit as x approaches 1, that should be equal to 2 as well. So there's a good final answer, and we got that using the numerical method. Okay, let's look at one more example using the numerical approach. So, and this limit, we probably want to memorize this. This will come up again. We'll give a formal proof of the fact, but for right now, we just want to plug in some numbers just to sort of get a feel for what this thing looks like. So we want the limit as x approaches 0 of sine x over x. And we can probably glean a little bit of information by looking at the graph of sine of x and y equals x. So let's look at that. So here's the curve sine of x, right? The standard sinusoidal curve. You saw what this looks like in a trigonometry course. And then here's the line y equals x. So when we are close to 0, so let's tune out the noise away from 0, and let's just focus in this interval that's close to 0. We can see that the sine curve and the line y equal x, those things are roughly the same when we are close to x equals 0. So sine of x is roughly the same as y equals x when we are close to 0. So if the numerator and the denominator are roughly the same, what should we expect for the fraction of these two things? So if a is very close to b, right, if a is very close to b, then we should expect that the fraction a over b is very close to 1. So we guess because sine of x is very close to x when we are near 0. The same is not true when we get away from 0, right? Then now we get a lot of divergence. But close to 0, sine of x and x are roughly the same. Therefore, the fraction sine x over x when we are close to 0, we should expect to get 1. So when we go through our numerical process, at the end of it, if we get something that's not close to 1, then we should go back and check our work again. Okay. Okay, to compute the limit as x approaches 0 sine x over x using the numerical method, we want to look at values of x that are close to 0 but not equal to 0, and we want to check on the left and on the right. So here are some values close to 0 but to the left of 0. And so when we plug these numbers into the function, here's the table of values that we get. And you can see that this table of values tells us what the limit is as x approaches 0 from the left. So here, this tells us that the limit as x approaches 0 from the left, that's just equal to positive 1, right? We can see this list of values is getting very close to positive 1. And then the same thing here. So now we've got some x values to the right of 0, but still very close to 0. When we plug these numbers, we get the same thing as we got over here. That's because we've got an odd function over an odd function, so that's even. In other words, it has y-axis symmetry. You could exploit that symmetry and save yourself the computation of one of these columns. But anyway, this tells us that the limit as x approaches 0 from the right, that is also 1. So the limit as x approaches 0 from the left is 1. And that's the same thing as the limit as x approaches 0 from the right. And so now, because the left-hand limit is the same as the right-hand limit, that tells us that the limit as x approaches 0, right? So the limit as x approaches 0 of sine x over x, that is just equal to 1. So that would be a good final answer using the numerical method.